Good morning, everybody. Welcome to today's expert webinar event, Synchronous Motors and Exciter Controls. A couple of items before we begin. Today's presentation is being recorded and will be available for on-demand viewing using your registration login or on our Basler Electric YouTube channel. Handouts are available for participants in the handout section of this presentation. Please enter any questions into the question section on the right side of your screen. Gene will answer any questions at the conclusion of his presentation. Any questions requiring follow-up will be answered by email. Be sure to follow Basler Electric on Facebook and LinkedIn to stay current with developments happening in our organization. Finally, future webinars are posted on the basler.com events page. All webinars are free to attend, but registrations are limited to 200 participants. Our resident expert, Principal Application Specialist Gene Asbury, will be discussing synchronous motors and exciter controls for power factor control, limiting functions, and advanced protection system. Gene will share his insights and experience on these critical systems and dive into the field application techniques for slip ring motors and brushless exciter motors. Gene, take it away.
Thank you. Good morning, or I should say hello, everyone. As John said, I'm a principal application specialist for Basler Electric. Been with Basler for 36 years now. So at this time, I'm going to start my presentation. Hopefully I can do this correctly. Can everybody see my screen? Let me go back one.
We're getting no's.
Oh. John, can you see my screen?
I cannot.
Okay.
While you're waiting for doing that, I'm going to go ahead and push a poll out to everybody.
I think I know what I did wrong. So
there we go. We can see on your screen now.
Yep, I think everybody can see my screen now.
Yes.
Apologize for that technical difficulty, but today we're going to talk about synchronous motors, the basics. I could probably do a presentation of synchronous motors that would take 2 to 3 hours to really do it justice. So we're going over the basics, going over some of the Basler solutions to control the power factor of the bars, depending on what type of motor it is. From there, let's start the presentation. This is a cutout view of a synchronous motor. You've got your different parts of it. You've got your rotor and your rotor windings, your different poles. You've got your stator windings. And then you've got your amortisseur winding, also known as a squirrel cage or a damper winding. And just like in induction motors, this is the winding that really causes the interactions between the RMF of the stator. When power is supplied to a induction or synchronous motor, there's an RMF that's developed that's at the frequency of the power being supplied. So you need something to start the motor. So the interaction between this amortisseur winding and the RMF that's generated will start that rotation of the motor. And since typically the synchronous motor isn't self-starting, you need that squirrel cage winding to get that action to take place. Also, what makes induction motors different than, or what makes a synchronous motor different than the induction motor is a separate source of excitation that is provided to the field winding to interact with the RMF of the stator winding. So as it approaches synchronous speed, and you would need some outside source to excite the rotor winding or the rotor field to pull that rotor into step with the stator field. And that's done by using different relays or control elements that we will talk about in the near future. So this kind of illustrates what each part is actually doing. The spinning center, the rotor is being interactive with the squirrel cage winding and the RMF that's being developed from the power supply to the stator windings. So as that the rotor is spinning and it links into synchronism, the excitation is providing, or the outside excitation supply that is being applied to the field winding is going to create that flux, or the energy needed to keep that into synchronous speed. So the things that would cause a synchronous motor to pull out a step would be something like a motor overload, a load that is applied to the motor that can't handle that load, or a low supply voltage. Let's say if this is across the line started and that supply voltage goes low, that could create a out of step sequence or a low excitation from your control device. Some of the differences between the induction motor, induction motor operates on electromagnetic induction, so it needs an interaction between the RMF created by the stator windings and the power supply and the rotation speed. So you need some sort of an interaction there to create the torque needed for the process. So that's why the rotor speed is always going to be slower than the RMF of the stator windings. So at that time, the induction motor is always using that magnetizing current from the power source to provide torque to the process. Synchronous motors' advantages is the fact that it runs at synchronous speed. For slow speed machines, like let's say 600 RPMs or less, synchronous motors can be much more efficient, and you can operate at a certain power factor by supplying field current to the field windings, and you can control your power factors as such. Some of the disadvantages of synchronous motors, they're more costly because now you've got a field winding that you don't have in an induction motor, and plus you have the controls to control that field winding, to regulate the power factor and all the other components needed to apply the field at that correct time. And also, some of the principle of operation of a synchronous motor isn't taught at many schools, so the workforce is not as familiar with synchronous motors as probably they should be. So let's talk about the field application for now. I'm going to kind of talk about two different types of synchronous motor. Mostly I'm going to talk about brushless excited motor, but right now I want to kind of talk about slip ring motors. And the difference is you don't have a rotating exciter on the motors. You're basically using an independent DC power source to excite the field of the motor itself. So in this application, you would have the synchronous motor, you would have some sort of a static exciter, DC power supply, or what. Back in the day, they would use like a DC power supply, ready to supply excitation to the field winding. And then you would have a field breaker, which is schematically noted here. And then you would have some sort of a relay, field application relay, to be telling the field contactor to close. And you also have a field discharge resistor, also known, sometimes they'll call that a starting resistor. So once the synchronous motor starts the process of coming up to speed, the field application relay is sensing right across the discharge resistor, looking at the slip between the RMF and the rotation of the speed of the rotor. And as that approaches synchronous speed, at that right precise moment, we're going to apply excitation and then remove that field discharge resistor from the circuit. And at that point, that's when the induction motor becomes synchronous. So now the static exciter is monitoring the motors, monitoring the voltage and the current to come up with a regulation point, controlling power factor. So we're looking at the real power being absorbed into the synchronous motor and the reactive power being supplied by the synchronous motor. And we come up with a cosine angle between the two, and that's what we're regulating to keep that power factor at a constant power factor. With synchronous motors, you can run at a unity power factor, you can run at a slightly or a leading power factor. So now you're generating magnetizing current out to the parts, out to the system. And if this is in a big industrial plant, this will recreate improved power factor, much like a capacitor bank would do. In a brushless synchronous motor, it's a little bit different, but the effects are the same. So now you've got your rotating exciter that's in the middle box. You've got your motor in the box to the right, and then you've got your field of the rotor in the box to your left. And our controls would be supplying excitation to the exciter field. And now you've got a control unit within the brushless exciter. You've got a couple SCRs, and keep in mind, this is one way to do it. Different motor manufacturers do it slightly different, but they'll have some sort of a control unit and some way, some means to apply the field at that right time. So as you can tell, the control unit is monitoring the field discharge resistor or starting resistor. And it once that motor starts to spin, there's an induced AC current across the field discharge resistor that is at synchronous speed. So as that starts collapsing to zero, the control unit would monitor that, and at about 97% speed, it will gate SCR2 that's in series with the field discharge resistor off, and it will gate SCR1 on. And so taking the FDR out of the circuit and supplying excitation through the AC alternator or armature being rectified through the rotating exciter or diodes on the brushless exciters, and applying field to the main field of the motor. So all of this is done pretty quick. You've got your motor starting time that you want to set your protection, and set the controller out here that's exciting the field. You want that set so that once that field is applied, the controller will go from a manual mode of regulation or running in what we call FCR mode, field current regulator. We would have that set to the full load capability of the motor itself. And when that field is applied, you're going to get that energy out to the field to pull that motor into step. And at that time, that's when it becomes synchronous. Everything's going like it should. The controller out here is regulating power factor. Now I'm providing excitation to that exciter field to maintain that power factor regulation set point. So here's a view of a brushless excited motor. Just shows you some of the components, the field discharge resistor, the SCRs and diodes, the exciter armature, the control module, that's the brains behind the operation. The critical part of a synchronous motor is applying the field at the right time. So this control module, and on slip ring motors, as we saw a few slides ago, it would be the field application relay that is applying that field at the right time. And that's when the Basler controls can take over and start regulating power factor. And they also have protective and control means to make sure that motor stays into synchronism. So power factor is an important part about a motor. So power factor is a ratio between real power and apparent power. It's expressed in percentage. So as I said before, we're really looking at, if we're regulating power factor, we're looking at the cosine angle between the real power and the reactive power. And that's where our set point target is at, maintaining that power factor. And I should say in most motors, in most motors that have a constant load on it, we're going to regulate power factor. On some motors, like a chipper motor, where the load is, always fluctuating. Some people like to use the bar mode of regulation, where it's looking at the bars instead of the power factor. Either one works, but like I said, for a constant load and things like that, power factor works the best. Options for large industrial power consumers that maybe have poor power factor at their plants and may even get penalized for it. They've got a couple options. They can purchase capacitor banks. They've got pretty expensive, and the only purpose is to give you power factor correction. But for some applications where a synchronous motor makes sense for that application, where you got a slow speed machine and you really don't want to put an induction motor out there because of the efficiency issues, utilizing the synchronous motor can perform the work that you need to be done, but it also can give you that power factor correction through a excitation system that can regulate that power factor. And even though your supply voltage may dip, we built these excitation system where they have forcing involved. So most of the time you think of forcing as something that happens with the generator. When you see a transient on a generator, you want to force the field to get that back to steady state voltage. But in a motor, it gives you the ability that if that line drops out there, let's say you have a 150% forcing capability on a synchronous motor, that will tell you your line voltage can drop by 50% and you could still maintain the process. So that forcing level gives you that advantage in a synchronous motor that, you know, a DC power supply cannot. So now we're going to talk about some of the Basler solutions. So Basler's been involved in the synchronous motor business probably for 50 years. I know back in the day we used to use our DC power supplies. We called them the MVC, manual voltage control, and we would actually bias, or we would put in what we called an SCP-250, which was a VAR power factor controller. So some of our engineers would develop these little pan chassis that would use some of these devices and maybe put some protective relays on there to look at give you a motor pullout protection. And we developed these packages, and they were ideal because that SCP-250 or the VAR controller, VAR power factor controller, would bias the MVC device, which is pretty much was just a DC power supply, and would bias it and regulate power factor. So we were doing that way back when. And then from there, we started using our digital products, you know, as they came out. You know, it was probably really got into it with the DEX 200 and then the DEX 250 and so on. So we've been doing motor applications for some time. Some of our products that we've used on synchronous motors, the controllers itself are the DEX 150, 250, not too much the 250N because the 250N is a negative forcing regulator. The only time we would use this is if it requires more than 15 amps and less than 20 amps. That's the continuous rating of the DEX 250, which is 15 amps, and the DEX 250N is 20 amps. The negative forcing doesn't give you much advantage on a synchronous motor as it does on a synchronous generator. So you and the expense, you just can't justify that added expense. The DEX 250E is basically taking the controls from the 250 and providing a bias signal to a 3 SCR bridge that gives us up to 200 amps of excitation. The 250E is ideal for slip ring motors that require much more field current than the brushless excited motors. So we've had a lot of success with the 250E on slip ring motor applications. Those are the controllers. The kits that we've got are called the SMC 150 and 250, using these controllers, and they're prepackaged, engineered solutions for synchronous motors and been very widely popular, even with the OEM. People have developed specialized system, but these two up here are right out of our catalog. They're already pre-engineered and they give you a lot of capability for your synchronous motors. We do have a SMC 250N. It is a custom design, just like the DEX 250E and well, that should be DEX 450, but I apologize for that. I thought I changed it. I must not have saved it, but this should be a DEX 450. Same way with complete excitation systems. And what we mean by that is excitation systems built in NEMA 1 enclosures or NEMA enclosures that is designed for a specific specification. And once again, that should be a 450. So some of the other features and functionality is we kind of talked about the auto mode, which is power factor or VAR regulation. we kind of talked about the manual mode, which is our FCR, field current regulator. And then some of the limiters, it's kind of interesting. The two main ones are the overexcitation limiter, that the controller can provide that added protection to make sure you don't overexcite the field. And we would tell the summing point of the regulator to back off if it starts hitting that limiter. And typically we would put another device out there called the ES74 relay that's looking off of the field shunt, and that's for an extended overexcitation protection. And then the DEX products have protection that you can set up for field over voltage or field over current protection. So there's a lot of tools to use to protect that motor and make sure that it stays into synchronism so you don't lose your process. Same way with the under excitation limiters. So that's set up where it's looking at bars being absorbed into the machine. As you start losing synchronism, the UEL will come into play before your protection will come into play, and try to save that process. Stator current limiter, I don't see that much on synchronous motor applications. And then some of the protection, loss of sensing is a nice one, because it looks at the PTs, and if you lose a fuse on a PT signal, instead of losing your process, the DEX products is smart enough to sense that, switch it to manual mode of regulation, and since the manual mode is tracking the auto mode, it would be bumpless transfer, and that process would be saved. You can even send a output out to the control room to say, hey, I just switched to manual mode, so you won't be regulating power factor anymore, but as long as the load is constant and you got power input, you should stay at that same power factor. But you alert your operators to say, hey, I might have to look at that and adjust excitation once in a while. And then you've got other protection, over and under voltage, frequency, reverse power, reverse VARs. These are used a lot in motor application, field over voltage, field over current. Sometimes it's a protection, sometimes as a permissive to do something else. And then for brushless applications, you've got your exciter diode protection. That's basically looking at the frequency of the field, the ripple frequency of the field, and can determine if one of those diodes in the brushless exciter has opened or shorted. And then you've got configurable protection. So anything that you're monitoring within the DEX cabinet, you can set up your own protection. So it gives you that flexibility. Some of the best comms plus software tools would be, your programmable logic, very easy to use, some real-time monitoring, oscillography and sequencing events are a very good tool for troubleshooting. Had a customer the other day was looking at the sequence of events. He wanted to know how to download the sequence of events, so I gave him a little procedure, and it was on a motor application, and so that all that data is available to you with the digital controls. Communications, you got a lot of different options. Modbus, either through RS-485 or TCP/IP. Most of these controllers are interfaced with USB ports for the PC interface to use our best comms plus. 232 ports, and then some CAN bus for expansion IO modules if you need more IO in your application. then you can use that. Here's a one-line diagram of a typical DEX 250 working into a brushless excited motor. You do have an optional BE111M, that's our motor protection relay right now, with an RTD module. So we could set up a complete system that includes protection, controls, remote display. So we have a lot of different options. Like I said, this is optional. If we replace this, we would replace it with a single element protection function called the ES55 relay, which is your motor pullout protection. And that's what that looks like. So it's a little DIN rail mounted device. Some of you, if you're familiar with the Basler products over the years, we used to have what we call a PRP 320, which was a motor pullout protection relay and was very popular. But we had to come up with a replacement. We had to obsolete the part. So this product for us is doing very well. And here's some of our pre-engineered panels. The SMC 150, capable of 10 amps continuous, and then the SMC 250 with the optional BE111 protection. So that's capable of 15 amps. So you got some small relays down here, the ES55, and then the ES74, that's your shunt protection for over-excitation and under-excitation protection. We do have an order form, how to order the SMC 250 or the 150. So these are catalog, pre-engineered circuits that has been very popular for us. And some other SMC options is SMC stands for Synchronous Motor Controls. So I just wanted to, I know we like to use a lot of acronyms, and so I try to tell them what they're all about. So this is a special DEX 250 with an 11M cabinet that we designed for one of our customers. So it has a lot of features and functionality in it. We do all of our cabinets in Highland, Illinois. We make all of our controllers either in Highland or in some of our relay cases, we make them in Taylor, Texas, which is a redundant factory for us. We build our own transformers. So that's your power transformer to supply power to the DEX 250. Then some of the control relays and things like that. Static solutions. So when you need more than 15 amps or more than 20 amps, when you're working into a slip ring motors, the DEX 250E is ideal. It can go up to 200 amps along with the right power transformer and the right field application relay, field contactor. We can make some very nice synchronous motor units for slip ring motors that will need, anywhere from 50 to 200 amps. We've done a lot of work with the water districts out west on their large synchronous motors driving pumps. So if you need more than 200 amps, we can go with the DEX 450 synchronous motor controller. And basically, it's just like, all of our controllers can work with synchronous generators or motors. This 450 is using, I'm thinking this is a 400 amp half wave conversion bridge. So it can only force in the positive direction. It's got a freewheeling diode on the output. You got a field application relay here, and I don't see a discharge resistor or a starting resistor. So they they probably reuse the existing starting resistor because that's a very crucial part of that motor. You know, that's a specially designed resistor just for that motor. And so if a customer wants us to replace that starting resistor, we have to give the exact measurements of that resistor so we don't affect its how the motor starts. You know, you want to provide enough synchronizing torque during that starting process, but you don't want to overheat it. So it's very, very crucial part. Some of the Best Comms Plus, very intuitive program, gives you a lot of information from our control panels to configurable protection. Best Space, you can do a lot of metering using our oscillography to do step responses or to capture triggered events. You know, if you got a situation and you want to, if you triggered on certain things like the motor stopping, you can grab that data and see what everything was doing. Maybe, you know, the reactive and real power, the field voltage, the field current. You can capture up to 6 parameters and you can see what was going on during that event and before that event. So it gives you some pre and post data that's programmable. Our real-time chart recorders gives us the ability to look at the system while we're doing response tests. The sequence of events is a great troubleshooting tool. Gives you you know, everything that motor was doing for the last 2,000 events. And then the programmable logic. A lot of this stuff will be gone over in the next, probably in a month, where we do Best Comms Plus training for the excitation control devices. And then Basler excitation control solution for synchronous motors with the 250. Probably the most popular type is the DEX 250E for slip ring motors and the DEX SMC 250 for brushless excited motors. Those would be the two. We have used 450s and its predecessors, the 400s, on many applications that require more than 200 amps. And then the DEX 150 is ideal for certain motor applications. You don't get all the features and functionality, but for small motors that are brushless excited, it might be ideal. So with that said, I went a little bit over, but is there any questions?
Thanks, Gene. Yeah, if anybody has questions, please use the questions tab on the right side of the screen to enter your question, and we'll have Gene answer it. We did have one come in through the chat. It says, what is the time resolution on the SOE timestamps? Also, can you elaborate on the maximum resolution between analysis and real-time recorder, time or magnitude-wise?
Well, on the oscillography, we're sampling every 4 milliseconds. That's the fastest we can do with the DEX 450, 250. So there's 1,200 data points out there that we record, and then it's a 4 millisecond time lapse in between data points. The resolution on the sequence of events, I'm not sure about that one. I'm not sure if I understand that question, but it's going to record every event. Like if someone activates an input or output, it's recorded. If the controller hits a UEL limiter, under excitation limiter or an over excitation limiter, that's recorded. So it's more or less a tabular list of everything that motor did, that or that controller did, and it's all time stamped and dated, so it's a great troubleshooting tool.
Great. We got a couple more coming in on the chat. What are lead times, especially for the DEX 150 SMC?
Well, that's a good question. I wish I had a marketing guy here. Unfortunately, the SMC 150 uses the DEX 150, and we've been having supply chain issues for the DEX 150. So it's hard for me to tell you when that's going to be resolved. I could tell you that the SMC 250 is definitely available, and the lead time there can be anywhere from 8 to 10 weeks, depending on our manufacturing load. I hope that answers your question. I really can't give you an answer on the SMC 150, but if everything was back to normal, it would be probably 8 to 10 weeks. But good question.
Good question.
Hopefully I answered that in a good way.
All right, we got another one. Is there any Basler's technical system to monitor field current and voltage in the brushless systems? I mean, for the rotating part of the system.
That's a good question. I'm assuming he's talking about going into the main field of the motor, and if they give us a shunt out there or something, we could do it, but I've never seen one. All we can do is monitor the motor output and the exciter field. On some large generators, brushless generators, I think Westinghouse used to put a shunt out there so you could monitor the main field also.
Okay, another one. Is the DEX 250 suitable for a 13,500 horsepower motor, 480 amps, or do you need a larger one?
No, that's a great question, because it really depends on the brushless exciter. If the brushless exciter on that motor is within the 15 amps, then yeah, you can use the 250. It all relates back to what that field of the brushless exciter is needed to maintain full load capability. I've seen DEX 250s on larger motors than that.
Okay,
So
looks like
another
there's
good question.
Second half of this question. Who defines the parameters of excitation system, the suppliers of the motor or the supplier of the excitation system? And which information is needed to do so?
The supplier or the motor manufacturer will design the brushless exciter in the motor. So they're the ones that will come up with the field data. So let's just take a WAG machine out of Minneapolis, the old EM. If you have an EM machine and you need to know what the rating of the brushless exciter is, they would have that data. Same way with like a Tico or a T-Mic.
Okay. All right, next question. What happens to the exciter panel DEX 250? Is it required to start the synchronous motor using a soft starter?
It doesn't need to. It can, but what happens is the stroke cage winding will actually start the process with the interaction between the RMF that's generated when the AC supply voltage is applied to the stator winding. So the interaction between the squirrel cage winding and the RMF will start the rotation. And then from there, it'll come up to synchronous or approach synchronous speed, and then someone will tell us to apply the field either through a control unit that we discussed earlier, or maybe through a speed signal.
Okay. One more. For how long can the 250N be at 20 amps
Continuous.
continuously? Okay.
Yeah, within reason. If you put it outside and it meets all the environmental regulations that we set forth in our manual, then you're fine at 20 amps. If you put it in an air conditioned room at 25C, you might be able to get a couple more amps out of it. But if you put it at a very high elevation, elevation and heat it will make you derate the machine. But everything that we manufacture is regulated. I think the Dex 250 is probably at 50 degrees C. So if it's within the parameters of the controller, it will be able to produce 20 amps continuous.
Okay, great. I see we've got a couple more coming in. We're at time right now. So I just wanted to remind everybody, we do have a Best Comms Plus presentation scheduled for September 16th. That's on the current schedule. Just watch your emails and our events page. We'll send information out when that's coming up. Again, future events are posted on the basso.com events page for all of our upcoming webinars. We are on Facebook and LinkedIn. Be sure to check that out to make sure you see our most current communications. In about an hour, this presentation will be on demand. You'll receive an email with a link to get to it. After that, we will post it on our YouTube channel for viewing. Again, thanks for everybody who attended today. And like I said, we'll have follow-up questions answered in emails directly to you. All right. Well, thank you very much, Gene. I appreciate your knowledge.
All right, thank you, everyone.
Helping us out. All right. Take care.